we've been talking about molecular orbital diagrams for main group complex, so we've been focusing mostly on s and p orbitals. But now let's move on to coordination complexes, which are complexes of the transition metal, so the D block. So now we have even more orbitals to deal with, and also a greater range of possible geometries. So here's some notation. We'll talk about MLN compounds. So M is the metal, L is your ligand, and then N is the number of ligands. So a metal complex can have a huge kind of range of ligands. You can have 2 ligands on it for a linear complex, or you could have 3 ligands, 4 ligands, 5 ligands, 6 ligands, 7. It depends on your metal and also on the ligand and how many you can fit around it. One thing to keep in mind is that it's often best to think about the ligand to metal interaction as dative. This is just kind of a picture. So there are greater degrees of covalency. But the reason this is useful is because counting the number of electrons involved in your complex is really important. Those of you in organometallics have already seen this. So for example, if we have a complex with a formula MClCO5, let's make it a manganese compound. So when you want to count the number of electrons when you're filling up your molecular orbital diagram, you have to know the oxidation state of your compound to know the number of d electrons. So in this case, here, if you want to think about Cl, the chlorine atom has 7 valence electrons. But if you want to think about it as a kind of 2-electron donor, we have to add a second electron here. And so this will be overall Cl minus. And this is how you would then donate into your manganese like so, for this to have the 2 electrons to act as a Lewis base. So that's why we think of chloride is an X-type ligand. So it's negatively charged. In comparison, if we want to think about CO, here's CO. CO already has a lone pair, so it can, without changing charge, act as a Lewis base. So therefore, this is what's called the L-type neutral donor. And therefore, if we have only one X-type anionic ligand in this complex, we have 6 ligands, so there's 1 chlorine and 5 carbonyls. This is still going to be manganese 1. And then this will be, therefore, D6. So this notation means that we're talking about the number of d electrons, and this is the number of total valence electrons remaining, so 6. Because manganese is in the 7th column on the periodic table, and then this is how we can calculate the number of electrons. Which brings me to the second point, is that if you want to think about the number of d electrons, we can think about the kind of electron configuration for the atom. So suppose we have the cobalt atom. This is 1s2, so cobalt atom, let me be clear. So we're not talking about complexes yet, we have no ions, this is not charged. The cobalt atom has configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, how many? 7. So I've written it like this because as you're going across the periodic table, you have the 4s2 fills in first, and you have 3d7. But when we start thinking about metal complexes, we will think of it as when you start binding the cobalt atoms, then the s orbitals are no longer lower in energy than the d orbitals. So then, when you, for example, if we start oxidizing this, so let's say we have an ionic cobalt 2+, let's say 3+, then the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So we remove the s electrons first, and then we remove the d electron. So that's really important to keep in mind. When you're building an MO diagram, you don't have electrons in the 4s orbitals because the d orbitals, once we start putting ligands around it, become lower in energy. So when we start drawing a MO diagram, for example, if we're making an MO diagram and we have our metal on the left and then we have our number of ligands on the right, when you start drawing your atomic orbitals of the metal, you start with the 5d orbitals. So if this is a first row transition metal, so there'll be 3d, and then we have the 4s, and then we have the 4p. So this order is critical for making your final MO diagram, the d orbitals and the d electrons are here first. So my acronym for helping you remember this, so D below S below P, don't screw up. Because someone will inevitably get these mixed up, and then your MO diagram will be completely wrong. So here are your atomic orbitals of the metal. And then for the ligand, ligands are primarily, if we're talking about the sigma donating ligands, they're more electronegative than the metal. So in fact, these should be below. Here are my orbitals of the metal. Here are my kind of like sigma orbitals. Make sure that these are below, lower in energy, lower in energy than metal. Okay. And so this is the reason why when I said that this was manganese 1, that it's D6. So even though manganese has a 4s, so the manganese atom has a 4s2 3d5 configuration, which I remove the electron. We remove one electron from the s orbital, but that remaining s electron is in the d orbital when we think about binding ligands to it. So that's why it's D6. Okay. And the last important thing that to remember for drawing these MO diagrams for transition metal complexes, and we know what they look like. So keep this in mind. Here's my coordinate system. And then, so you have to be able to draw, the d orbitals. Excuse me. So here's dz squared, which remember is also known as 2z squared minus x squared minus y squared. And then we have our, let's say, x squared minus y squared, xy, xz, and of course remember these phases. So these are the important d orbitals that we'll be using for the next several classes.